Okay. Well, first of all, I want to thank the organizers for inviting me, for giving me the opportunity to present my work here. So I will talk on the one hand about alternating sign arrays, in particular about alternating sign matrices. And you can see an example of such a matrix on the first slide. And on the other hand, some Littlewood type identities, which are related to alternating sign arrays. And here on the slide, you see the classical Littlewood type identity, which says that if you sum the Schur functions over all partitions, then you get this very nice and simple product. So this is joint work with Moritz Gangl, Hans Höngesberg, and Florian Schreier-Eigner. Okay, how to turn pages? Okay. So here's my ambitious outline. I will first start with introduction. I will show you some well-known story about a missing bijection related to alternating sign matrices. So this is maybe something many of you know. Then I will talk about something that seems maybe totally unrelated. I will introduce some symmetric polynomials, which I will name Robbins polynomials. Then I will go back to alternating sign matrix objects. I will show you a rather new story about missing bijections. Namely, I will talk about objects called alternating sign triangles. Then in the fourth part, I will tell you what these Robbins polynomials that I've introduced in the second part actually have to do with alternating sign matrices. So they are a kind of symmetric generating function of alternating sign matrices. And then in the fifth and the sixth part, I will talk about related Littlewood identities, where, you know, the ordinary Littlewood identity is something about summing all Schur functions. And these Schur functions will be replaced by the Robbins polynomials, which are actually generalizations of Schur functions. And we will see some nice results there. Okay, so but let me start with a rather old story about alternating sign matrices and totally symmetric self-complementary plane partitions. So what is an alternating sign matrix? An alternating sign matrix is always a square matrix with entries 0, plus, and -1, such that in each row and each column, two conditions are fulfilled. So the first is that if you only consider the non-zero entries, then they appear with alternating signs. So ones and -1s alternate, and then the sum of entries is always 1. So for instance, look at the third row. If you disregard the zeros, then you see ones and -1s alternate, and also the entries sum to 1. So that's the definition of an alternating sign matrix. So here I've displayed the first few examples. So one important observation is that every permutation matrix is an alternating sign matrix because it fulfills this requirement. It simply has no -1. So that there's not much to alternate. So you have in each row and column 1, 1. And for order 1 and 2, these are all alternating sign matrices. But for order 3, there is one additional one, which has a -1 in the center. So you have the 6 permutation matrices and the one additional alternating sign matrices. And for order 4, there are already many alternating sign matrices that are not permutation matrices. Okay, so the alternating sign matrices have been enumerated. So it is known that the number of alternating sign matrices given by this very innocent looking simple formula. Why do I say innocent? Because the proof of this formula is very complicated. So it was first proved by Doron Zeilberger in 1996. It was conjectured much earlier by Mills, Robbins, and Ramsey, who actually introduced alternating sign matrices. I should say that actually in that paper of Doron, he proved something more general in a sense. So he had an additional parameter. And Kuperberg then proved the theorem as stated here, also with methods from statistical physics that involve something like the Young-Baxter equation. Okay, so this is what I want to say about alternating sign matrices about this point. Now I want to say something about plane partitions. So what is a plane partition? Well, you just look at this picture here. So a plane partition is always such a pile of cubes. And imagine the origin to be the corner of the box that you don't see. And then if you walk on top of the boxes away from the origin, then you will always go down. So that's a plane partition. More formally, you can define it as a subset of this Cartesian product if you want to define them as a subset of a times B times C box. And whenever a triple is in a plane partition, then also every triple with smaller coordinates is also in a plane partition. Of course, this triple encode the unit boxes in the bigger box. So that's a plane partition. However, I'm not interested in all plane partitions. I'm interested in very symmetric plane partitions. So let me explain what do I mean by that. So more precisely, I'm interested in totally symmetric self-complementary plane partitions. So first, let me tell you what is a totally symmetric plane partition. So it just means that, well, if you take a cube in your plane partition, which is encoded by a triple, by 3 numbers, and then if you permute these coordinates, then the corresponding cube also needs to be in a plane partition. So in a sense, it's invariant under the action of the symmetric group of order 3 if you permute the coordinates of the unit cubes. So this is what is meant by totally symmetric. What does it mean to be a self-complementary plane partition? Well, if you look at a plane partition in a box, and in this...
Sorry to interrupt. I'm not quite sure. I think McMahon did symmetric plane partitions, or maybe Andrews, and McDonald did totally symmetric.
Yes, but he defined
McMahon did just everything.
No, he did not prove the formula. I totally agree.
Yeah, I think it's Andrews and McDonald. For symmetric was Andrews, and for totally symmetric was McDonald, I think.
Yeah, I didn't mean to say that he proved the formula. It's just the definition. You also think the definition he didn't have this definition?
No, symmetric came from McDonald, the symmetric classes.
Yes.
He only proved about
absolutely true.
Distance without any symmetry. Okay, sorry.
Yeah, absolutely true.
Okay.
Okay. Self-complementary, this means the following. So if you consider a plane partition in a box, and in that case, it's a 2n times 2n times 2n box, then if you consider all non-boxes, so every box that is not part of the plane partition, it is a plane partition as well. So the complement of a plane partition in a box is a plane partition as well, with a different origin. And if this plane partition happens to be the same plane partition as the original one, then it's called a self-complementary plane partition. And I want to have all these symmetries. If I have all these symmetries, then George Andrews showed that the number of these totally symmetric self-complementary plane partitions in this box is given by the very same formula as the one for alternating sign matrices. And of course, if you see something like that, you really would like to have a bijection. You would really want to transform an alternating sign matrix in a certain way into such an arrangement of cubes. Such a bijection does not exist. Many people have tried to find such a bijection. I'm not totally sure that a simple bijection exists because, you know, people have tried a lot. There are a lot of refinements that could help you, but still it could be that there is a simple bijection. Who knows? Okay, so now I come to the second part, to these Robbins polynomials, and I define them by this bi-alternate formula. Okay, so let's look at what I did here. So I take here in this argument, you see a polynomial in n variables, x1 up to xn. You also see a few other parameters, t, u, v, and w. Then you see here an exponent, ki. So, but it is a polynomial in the xi's. Then I take the asymmetrizer of this polynomial, which simply means that I sum over all permutations of n elements. I permute the variables corresponding to the permutation, multiply by a sign. So this makes my function into an asymmetric function in the xi. And then I divide it by the smallest asymmetric function that is non-zero, which is this here. And it is very easy to see that every asymmetric function has to be divisible by this van Helmont product. And if I do that, I get a symmetric function. So if I divide an asymmetric function by asymmetric function, then it will be a symmetric function. So it's invariant under the action of the symmetric group. Okay, so that's a definition. You see 4 parameters, T, U, V, and W, which will be important. And you see these KIs, they will correspond somehow to what you know as the partitions in the Schur function. Okay, so and actually the Schur polynomials are a special case of these Robbins polynomials. There are several possibilities how you can specialize. So in principle, what you do is we had these 4 parameters, T, U, V, and W. And if you set all of them 0 but 1, and which you set equal to 1, you always get some Schur polynomial. So here I've written down the calculation. And the only important thing to see is that the asymmetrizer of such a simple function, so of a monomial, is always the determinant. And then you get the bialternate formula for the Schur function. So you can specialize Robbins symmetric polynomials to get Schur functions. Actually, the Robbins polynomials also generalize the whole Littlewood polynomials. In that case, you have to specialize 2 parameters to 0, and then the t has to be transformed to minus t, and the w has to be 1, and then there is some rational function in t, and this is how you get the whole Littlewood polynomials. But it doesn't matter for the rest of the talk. I just wanted to mention that they're also in this family of symmetric functions. So as you know, or maybe is the true polynomials are actually a generating function of semi-standard Young tableau. So that's exciting for combinatorialists that there is a combinatorial model underlying the Schur polynomial. So they are, in a sense, a generating function. So the first question I want to answer is whether there is also a combinatorial model underlying the Robbins polynomial. So is there some kind of tableau such that Robbins polynomials are a generating function of them? And I wouldn't be here if this was not the case. But actually, it's not so good to work with tableau. It's better to work with something that is called Gelfand-Zetlin patterns, which is actually equivalent to tableau. And this slide is intended to explain what Gelfand-Zetlin patterns is, but also indicates a little bit the bijection between semi-standard Young tableau. Okay, so Gelfand-Zetlin pattern is something very simple. So you can immediately look at the example here. So you have a triangular array of integers where you have a weak increase in northeast direction and in southeast direction. So as you have it here. So that's very simple. And then we have a weight associated to Gelfand-Zetlin pattern. So this is the weight here. So it's a weight which has n variables, and the exponent of the xi is the following. So you sum the elements in row I and you subtract the elements in row I minus 1. So that's the weight. And then the Schur function is actually the sum of all weights of all Gelfand-Zetlin patterns with this particular bottom row. So what you do is you write the partition in reverse order, and if it doesn't have n elements, then you add some zeros in front. So in total, you want to have n elements in this sequence, and then you look at all Gelfand-Zetlin patterns with this bottom row. So that's another combinatorial model of Schur functions. And here I try to indicate the bijection between Gelfand-Zetlin patterns and semi-standard Young tableau, if you know this definition of Schur functions. So it's the following. So this semi-standard Young tableau corresponds to these Gelfand-Zetlin patterns, and the bijection is the following. So if you look at the ith row of the Gelfand-Zetlin pattern, then this is the shape in reverse order of the entries less than or equal to I in a semi-standard Young tableau. So for instance, let's look at the fourth row of the Gelfand-Sedlin pattern. So, and if you read it in reverse order, it's 7, 5, 3, 1. And then what you have to look at, because you're in the fourth row, you have to look in your semi-standard Young tableau at all entries less than or equal to 4 and look at the shape. So in the first row, there are 7 entries less than or equal to 4, which corresponds to the 7 here. There are 5 entries less than or equal to 4 in the next row. And here you see how this fourth row of the Gelfand-Sedlin patterns is arising as a shape of the semi-standard Young tableau. And that indicates what the bijection is. Okay, so here I've done an example how to compute the Schur function of the partition 4, 2, 2. You take all Gelfand-Sedlin patterns where you take the reverse partition. And then, yes, you compute all of them, you compute the weight, and then you sum the weight, and then that's how you get the Schur function. So that's a Gelfand-Sedlin patterns are a combinatorial model for Schur functions. So now I want to show you, so what was our goal? So we had this Robbins polynomials, and we wanted to find a combinatorial model of these Robbins polynomials. And I will first do the case t is equal to 0. Okay, so there were these parameters t, u, v, and w, and I start with the case 2 is equal to 0 because that's a very neat case. And actually, you can immediately look at the example below here. So so you have a Gelfand-Sedlin pattern again. So again, you have weak increase in northeast and in southeast direction, but there are certain decorations. Okay, so every entry of this Gelfand-Sedlin pattern is decorated with some arrows. In fact, every entry has to be decorated either by a left arrow, by a right arrow, or by a double arrow. And the meaning of these arrows is that if an arrow from a lower element is pointing to an upper element, then these entries must not be equal. So this is what I wrote here in the summary. In principle, we again have a weak increase in northeast and southeast direction, but we have the additional requirement that an arrow indicates strict increase. And this is also what I wrote here in a more complicated way. So we have for each little triangle, x, y, and z, we have the condition that, for instance, if the decoration of x is a left arrow and the decoration of z is a right arrow, then y has to lie in the interval x, z. But if the decoration of z is actually pointing towards the y, then the y must not be equal to the z. So this is where we require a strict increase. So the arrows really tell you that that you have to have a strict increase at that point. So that's arrowed monotone triangles. And then I also have to introduce a weight. And it's very similar to the Schur weight. So the black part is actually the Schur weight, which is the differences of the ith row and the row I-1. But then you need to take also into account the decoration. So the u, v, and w takes into account for the number of right, left, and double arrows. And then also you need to, the exponent of the xi also involves a number of right arrows in row I minus number of left arrows in row I. And then the result together with Florian Schreier-Eigner is actually that the generating function of arrowed monotone triangles is given by this Robbins polynomial at t is equal to 0. So we have a combinatorial model of these symmetric functions that I have defined at least for the case t is equal to 0, and it's very similar to what we have for Schur functions, but we have some decoration, so that's the only difference. But I also want to show you the case when t is general, so when it's not necessarily 0. But for that, I first need to actually generalize what I've just shown you. So in the example that I've shown you, the bottom row of the monotone triangle is always strictly increasing, actually. One can generalize this as follows. So what you do is you involve signed intervals. So here I define signed intervals. So it's just the ordinary interval if A and B are in order. So if A is less than or equal to B, and if they are not in order, then you interchange them and you add one to the second one and subtract one to the first. And that's then also an interval. But in the case when B is equal to A minus 1, it's just the empty set. So that's a signed interval. And now, and if you're in the second case, then you say that the interval has sign minus 1. So you give this second case where you have swapped, you give it a sign. And then you can actually just take this definition here, and that's the reason why I wrote it in this way with the interval. You can take just simply this definition here and replace all intervals by signed intervals. Then you have to, and that's what I've written here, and then you also have to modify the weight slightly. You only have to introduce a certain sign. You count the number of intervals with negative sign. So that's a slight modification of the weight. And with this now, you can actually get a combinatorial model for the Robbins polynomial, also if the sequence was not strictly increasing. And here actually is an example. So one has to check these examples actually quite carefully because of this signed interval. And whenever I have this curly double arrow, it means that the corresponding interval has negative sign. And with that, now it's quite easy to look at the general case. So our goal was now to have a combinatorial model of this Robbins polynomial for general T. So what's the difference now? So the difference now is also that you allow no decoration. So you can again immediately look at the example at the bottom. So you see some triangular array of integers that have decorations, but some of them have no decoration, which I also sometimes indicate by it is decorated by the empty set. And then you have you can extend the definition that I've shown you before of arrowed monotone triangles. And if you do it that way, then you actually get the full theorem, which gives you a combinatorial model underlying these symmetric Robbins polynomials also for general T. And how you need to change the weight now is indicated in orange here. You also need to take into account how often you give no decoration, or equivalently how often you decorate with the empty set. So that's the general theorem. So now you might wonder, why did I first tell you about this sign thing before I moved to general T? So one could think that maybe if rows are weakly increasing, you're always with positive intervals. You don't have to interchange the boundaries. There's just one case that can happen where this is not true. So for instance, it can happen that in a row, you have twice the same entry, and from this, the left entry, you have an arrow pointing to the right, and from the right arrow entry, you have an arrow pointing to the left. And then the rule would tell you, well, because you need to have strict increase here, you need to add 1 to the x, and you need to subtract 1 from the second x. But then this is not a real interval anymore. And then you have to interchange the left and the right boundary. You have to add 1, subtract 1, and then you actually see it's this interval, and which is simply the set that only consists of x. So that's the one thing that can happen in the case t is equal, in a general case when t is not equal to 0, and that's why you need to have signed intervals. So that's why I had to do that. Okay, so what I've done now is I've defined these symmetric polynomials, and I have shown you a combinatorial model, and especially the first case when t is 0, this will be important later on. But before I tell you that, I will move back again to alternating sign matrix objects. And this is actually a rather new story, but again about missing bijections. Namely, I will define alternating sign triangles. So they are very similar to alternating sign matrices. The only thing that has changed really is the shape. So we don't consider square shape, we consider this triangular shape. And you can immediately look at the example below. Again, the entries are 1, -1, and 0. And the first two conditions you know already. So the non-zero entries alternate in each row and each column. Then all row sums are 1. For columns, this is not what we want. So for columns, we want something else. So for columns, we have the condition in orange. So we want to have that the topmost non-zero entry of each column is a 1, if such a non-zero entry exists at all. So for instance, it can happen, as you can see in the example, that columns have no non-zero entry. So like, for instance, this column. But if there is a non-zero entry, then the topmost non-zero entry has to be a 1, which is fulfilled in this example. Okay, so that's a definition. And why are people interested in it? Well, first of all, I've given you now all the alternating sign triangles of order 3. And maybe if you remember, alternating sign matrices of order 3. So remember, we had the 6 permutation matrices and 1 additional one, I said. So where the -1 is in the center. And so do we have it here. We have 6 alternating sign triangles without -1 of order 3 and 1 additional one with a -1. And that's no coincidence. That's actually true for every n. So together with Arvind Iyer and Roger Behrendt, I showed that the number of alternating sign triangles with n rows is counted by the very same formula as alternating sign matrices. And the proof is not at all a bijective proof. It's again a horrible computation. And again, we have no bijection, so we don't know of any bijection. I mean, here it's even more mysterious because it's the same type of objects. You have alternating sign matrices and you have alternating sign triangles. So why can't you transform the one into the other? So far we can't. And maybe also maybe it's not possible to do this easily. But I can actually give you hints about how the bijection could look like if it exists by showing you some statistics that have the same distribution. And the first statistic, I will show you 2 statistics. So the first statistic is very easy. It just counts the number of -1s. So as you have seen in the example of n is equal to 3, there are 6 cases where you have no -1 and 1 case where there's 1 -1. So let's look now at the case when there is no -1, both for alternating sign matrices and for alternating sign triangles. And for alternating sign matrices, we know that if there is no -1, then this is simply a permutation matrix. And for alternating sign triangles, one can also show that the number is n factorial. And this is what I do on this slide, actually. I will try to convince you why also in this case we have n factorial many alternating sign triangles. So why is this the case? So first of all, what is an alternating sign triangle with no -1? So you have to have a unique 1 in each row, because one of the conditions was that all row sums have to be 1s. So there has to be at least 1, 1, and there cannot be more than 1, 1 because there cannot be a -1 in between. And then we have to have at most 1 occurrence of a 1 in each column. So for each row, you choose a 1, and for each column, at most 1, 1. So here's an example of such an object. And now we want to enumerate alternating sign triangles with no -1. And here it's really good to work from bottom to top. So in the bottom row, there has to be a 1, so there is no choice. So now what happens if we work from bottom to top, if we are in the ith row from the bottom? So what happens there? So in principle, this row has two I minus 1 elements, okay? So if you look at the array, but in principle, there would be that many columns to choose, but I minus 1 columns are already taken from everything what happened below. So what is left is I columns where you can choose to have the unique one in the ith row if you count from the bottom. So in total, we obtain also n factorial, but the other way. So we have one choice at the bottom, then we have two choices in the next row, three choices in the next row, and that gives you n factorial. Okay, so we have shown that if we ask for the alternating sign triangles with no -1, then this number is n factorial. But actually, this is true not only for 0, but actually for every non-negative integer. If you ask for all alternating sign matrices on triangles where the number of -1s is m, then you get the same number. And that proof is, again, very complicated, much more complicated than what I've just shown you, and a horrible computation. I will show you another statistic, which is the inversion number. So you can also define the inversion number of a alternating sign matrix, and it's just a generalization of the inversion number of a permutation. So here, that's a fancy way to write the inversion number. So if you encode a permutation as a permutation matrix row-wise, then if ones are in this relative position, then you have an inversion, and then you can think that you can think a bit and see that you can encode the inversion number like this. You can use this as a definition for alternating sign matrices, as for the inversion number of alternating sign matrices. And then actually you can take almost the same definition for alternating sign triangles, except that you have to modify the range because it's not anymore a square, it's a triangle. And then actually it is true that if you look at the joint distribution of the number of -1s and the inversion number, you get the same for alternating sign matrices and for alternating sign triangles. So you have now two statistics that have joined the same joint distribution. So that could give you a hint that in this bijection that we are missing, these statistics are mapped to another. So here I've shown you the case n is equal to 3. In this case, there is not a unique bijection that preserves the statistics. So for this pair, you could either map this alternating sign matrix to this alternating sign triangle or to this, and there's another pair of this type. But it already gives you some information. Okay, so but now I need to tell you, what do alternating sign matrices have to do with these Robbins polynomials? And that's actually not very complicated. And in order to explain this, I need to work with a model that is equivalent to alternating sign matrices, which is actually called monotone triangles. So this is where the name arrowed monotone triangles comes from. So what is a monotone triangle? Well, a monotone triangle is a Gelfand-Zetlin patterns, and I try to indicate this by, we have a weak increase in this direction and a weak increase in this direction. And the additional requirement is that we have a strict increase along rows. So that is additional one. And here you can actually see an example of a monotone triangle. So it's weak increase in this direction, in this increase direction, and strict increase in rows. And here is actually how I transform my alternating sign matrix into such a monotone triangle. So there is an intermediate object, and you get that intermediate object simply by in the alternating sign matrix by adding all the entries that are in the same column and above to each entry. So for instance, this one is there because everything that is above adds to 1. And you always get a 0, 1 matrix that way. And then in order to go from this intermediate object to monotone triangles, you record row by row the positions of the ones. So in the first row, you have a 1 in position 2, then you have a 1 in position 1 and 4, and this is how you get the monotone triangle. And it's known that it's not hard to see that this is a bijection between alternating sign matrices and monotone triangles with bottom row 1, 2 up to n. And now I have shown you these arrowed monotone triangles before, and here I just repeat the definition. And just as a homework for you, I defined arrowed monotone triangles as decorated Gelfand-Tsetlin patterns, but one can really see that they are not only Gelfand-Tsetlin patterns because of these decorations, which force strict increase. If you require that the bottom row of an arrowed monotone triangle is strictly increasing, then all rows need to be strictly increasing. So actually, if you remove from an arrowed monotone triangle all the arrows, then you will get a monotone triangle. You will get a Gelfand-Tsetlin pattern that is strictly increasing. And even more is the following. So with this slide, I want to convince you, as soon as you know the generating function of arrowed monotone triangles, you can actually compute the number of monotone triangles in a very easy way. So when you set the parameter u and v equal to 1 and the w equal to -1 and all xi's you set them to 1, then you get from the generating function of arrowed monotone triangles the number of monotone triangles with a particular bottom row, with the bottom row k1, k2 up to kn. So this was also some parameters in the Robbins polynomials. So with the rest of the slide, I try to convince you that this is the case. So how should you think about this? Well, you fix a monotone triangle, just any monotone triangle, and you consider all arrowed monotone triangles that can be obtained by decorating the entries of that particular monotone triangles. So, okay, so there are 3 types of entries. One type of entries is when it's equal to its northeast neighbor, then that entry has to be decorated by a right arrow. Then the other side is when an entry is equal to its northeast neighbor, then it can only be decorated by a left arrow. And then there are the others that are neither equal to the left top or a right top neighbor, and that you can decorate with whatever you want. And let L, R, and F denote the numbers of these particular entries in your particular monotone triangle. And then you can, if you set all xi is equal to 1, you can easily see that the generating function of a fixed monotone triangle is then just given by this simple thing, okay? Because of what I've said before. And now if you set u equal to 1, v equal to 1, and w equal to -1, then you get 1 here. And then every monotone triangle actually has a weight of 1, which is what you want to count them. Okay, so what we can take from this slide is that if we know the generating function of arrowed monotone triangles, then we can compute the number of monotone triangles. But I've showed you the generating function of arrowed monotone triangles. These were these Robbins polynomials that I've introduced. Okay, so finally, I come to these Littlewood identities that I've indicated in the title of my talk. And well, first I consider the case that T, U, and V is equal to 1. Here, I indicate once again the classical Littlewood identity, which says that if you sum the Schur functions over all partition, you get this simple product here. And so that formula has a very nice bijective proof. So it uses the Robinson-Schoenstedt-Knuth corresponding, and it also uses its symmetry. And then in a work of myself and also of Hans Höngersberg, we noticed that a certain identity which looks very much like this is actually the key ingredient. So it looks as follows. So we sum all these Robbins polynomials for this special choice of parameters, then we also get a very nice product. So it includes the right-hand side of the classical Littlewood identity, but there are some numerators as well. And of course, this is exciting in a sense. So since we are missing bijections in the field of alternating sign matrices, we now have an identity which is in a sense a key in a certain enumeration. And we could try to, invent some RSK to prove this identity. We even have on the left-hand side something which is a combinatorial model very similar to Schur functions. And the right-hand side also has a very simple combinatorial interpretation in terms of decorated two-line arrays, which in the ordinary case of a Littlewood identity, you have just ordinary two-line arrays. So together with Moritz, Hans, and Florian, we have constructed RSK-like bijective proof of this corresponded in the special case when W is equal to 1. Then I want to say something about bounded Littlewood identities. So in the classical case, there also exists a bounded version of the Littlewood identity, which just means that you bound the parts of the partitions. The right-hand side is not anymore a simple product. It is this determinant divided by a product. And one other result is that there is such a bounded Littlewood identity also for these Robbins polynomials with the very same specialization. It's also it's very similar looking, except that the determinant in the numerator is more complicated. The proof is rather lengthy. It has 7 pages, but it's all elementary. It has several applications. One of them I'm somehow indicating here. So actually, Moritz has used this to relate a very refined counting of alternating sign triangles to a very refined counting of totally symmetric self-complementary plane partitions, which again could give you a hint what a possible bijection looks like. And the significance of this result is that there are similar conjectures, old conjectures of Mills, Robbins, and Ramsey and of Grattenthaler for the ASM TSCCP relation that is still a conjecture, so that are still open. But for alternating sign triangles, this identity allowed us to prove similar results, or allowed Moritz to prove similar results. Then another application of the bounded Littlewood identity. So if in this identity, here, you set all xi's to 1, the w to -1, and the m to n-1, it turns out that both sides, you get these numbers. And well, what's so nice about these numbers? Well, these numbers are round, so they only have small prime factors, and you can express them by this formula. So this will be a consequence of something I show you below on the next slide. Actually, our theorem involves the additional parameter m, so you don't need to specify. But what is interesting is that rather recently, this sequence also appeared in work of Di Francesco as the number of certain statistical physics model, the so-called 20 vertex model. And he showed in that paper that they are counted by the same formula as domino tilings. He did not prove the formula. He showed that they are counted by a certain determinant and conjectured that this determinant is equal to this product. And after that, Christoph Kutschan could actually evaluate this determinant and show that this determinant is equal to this simple product formula. So it's kind of mystery that these numbers now appear here and there. here I show you the result that I promised. So we showed that if we set all xi's to 1, the w to -1, then this expression in this bounded Littlewood identity is just this simple product formula. And this really enumerates something. So this is a certain -1 enumeration of Arrowed-Gelfand-Zetlin patterns. But actually, we could also find a signless version, so we could cancel positive and negative objects and see what remains. So, and it is now an open problem to find a bijection between these 20 vertex configurations of Di Francesco for the special case m is equal to n-1. So that's an open problem, and then other application of the bounded Littlewood identity. Then very briefly, I will tell you something about another case where we have a Littlewood identity and actually also a Cauchy identity in that case. So I was just considering the case T is equal to V is equal to U is equal to 1, but now we are considering the case T is equal to 0. And in that case, so this is about papers that are about to be written. But in that case, we also have some kind of Littlewood and Cauchy identity. So let's look at what I've written here. So in the first theorem, I sum over all Robbins polynomials. Now I only specialize T to 0, and I get this right-hand side. So on this right-hand side, you see everything that is in a usual Littlewood identity, but you see an additional polynomial here, which is actually a symmetric polynomial. And it's actually a symmetric polynomial that has several nice properties. It has a nice Schur expansion. Then on the other hand, one can also look at the corresponding Cauchy identity, which just means that you take the product of two Robbins polynomials with the same parameters ki. You swap the u and the v. So here if you have u and v, and here you have v and u, you get this right-hand side. So what you see in the denominator is just what you have in the ordinary Cauchy identity. And then the numerator is also a polynomial with several nice properties, and a polynomial where we have a formula for, so in terms of a determinant. But this is work in progress. And in this, I want to end my talk and thank you for your attention.